Bismillah Rahman Rahim. Welcome everyone. Today we are going to start a very basic topic of the chemistry, that is the intermolecular forces. Now let us discuss first of all the characteristics of the intermolecular forces. These are the forces which are present between molecules of a substance. So these are intermolecular, mean they are present between molecules of a substance. They are not interatomic forces that are present between the atoms. Interatomic forces are actually the intramolecular forces, which are present between two atoms or which hold the two atoms together, like covalent bond, ionic bond, metallic bond, coordinate covalent bond. These are the intramolecular forces. But these are the intermolecular forces that do not hold the atoms together, but they hold the molecules of a substance together. They are relatively weaker forces as compared to the intramolecular forces, ionic bond and covalent bond. They are no doubt stronger as compared to these intermolecular forces. They affect physical properties of a substance. In fact, at the macroscopic level, the idea of the intermolecular forces comes from the physical properties like study of boiling point, vapor pressure, viscosity, surface tension. These properties at the macroscopic level provide the concept of the intermolecular forces and their relative strength. So they affect physical properties of a substance. They do not affect the chemical properties. They have no direct relation or dependence on the electronic configuration of the atoms. You know, ionic bond, covalent bond, they are related to the electronic configurations. They are related to the octet, duplet, but they do not, intermolecular forces do not have any relation with the electronic configuration, especially the valence shell electronic configuration of atoms. So these are the characteristics of the intermolecular forces. Now let us discuss their examples one by one. First is the dipole-dipole force. What is a dipole? A dipole is actually a polar molecule. Di mean two, pole mean parts. A polar molecule always has two parts, one partial positive and one partial negative. So a polar molecule is called as dipole. Now dipole mean there are two polar molecules and these forces are present between the two polar molecules. Actually, the positive end of one polar molecule attracts the negative part or end of the other polar molecule. Just like the partial negative chlorine atom of one molecule attracts the partial positive hydrogen atom of the other molecule. So these forces are the dipole-dipole forces. Now look very carefully. This red dotted line, it is the force between two molecules, while this black solid line, it is the force between two atoms, hydrogen and chlorine atom. So this force will be intramolecular and this force will be the intermolecular force, and here the intramolecular force is the covalent bond between hydrogen and chlorine, while the intermolecular force is the dipole-dipole force. Now, it is very important that what are the factors that decide the strength of dipole-dipole forces. The strength of dipole-dipole forces is directly proportional to electronegativity difference between the bonded atoms. So greater the electronegativity difference, more will be the partial positive and partial negative charge on the atoms, and more electrostatic forces will be present between those partial positive and partial negative ends. Like dipole-dipole forces are strongest in HCl, then in HBr, then in hydrogen iodide. So that is the trend of the strength of dipole-dipole forces in the halogen acids. Why I have not written HF here? Because you know HF has hydrogen bonding, and I have already discussed hydrogen bonding in two separate lectures. If you want to study that, it is highly recommended to watch those lectures. Now the second factor is the intermolecular distance. The strength of dipole-dipole forces is inversely related to the intermolecular distance. Suppose that HCl is present in three physical states: solid, liquid and gas. So the strongest dipole-dipole forces will be in solid HCl because of the minimum intermolecular distance, and weakest will be in HCl gaseous form because of the maximum intermolecular distance. These are the permanent forces. Dipole-dipole forces are permanent forces because the dipoles are permanent. Now, second one is the ion dipole force. Its name indicates that these are the attractive forces between ion and a polar molecule. You know, whenever the ionic solids are dissolved in a polar solvent, and the best solvent for the ionic solids is water. So, I am discussing it with reference to water. When the ionic solids are dissolved in water, their ions get separated. Suppose sodium chloride is dissolved in water. So sodium ion and chloride ion, they are separated from each other. The lattice breaks down. Now the sodium and chloride ion both are surrounded by the water molecules, and this phenomena is called as the hydration. The water molecule will direct its negative end towards the positive ion, and the force of attraction between the ion, cation, and negative ends of the polar solvent, that will be called as the ion dipole force. Now, this force will definitely stronger than this force because here the forces of attraction are between partial negative and partial positive. But here the force of attraction is between complete positive and partial negative. So here the positive is partial, here the positive is complete because ion has complete positive or negative charge. So that's why these forces will be very strong forces. And this phenomena is called as hydration, and the energy released in this phenomena is called as the heat of hydration because the formation of forces is an exothermic process. And very important, this point is very important for MCQs, that these are the forces that are responsible for the dissolution of ionic solids in water. Sometimes it is asked in the MCQs that what are the forces which are responsible for the dissolution of ionic solids in water? Alpha, dipole, dipole, beta, ion dipole, Charlie, Debye forces, delta, London dispersion forces. So the correct answer will be ion dipole forces. Third are the permanent and induced dipole forces. This one is the permanent dipole. Permanent dipole mean that is a permanent polar molecule. Induced dipole mean the non-polar molecule which is in which the polarity is induced because of polarization, and that polarity is induced by the permanent dipole. So these are also called as Debye forces, and they are present between polar means permanent dipole and non-polar mean induced dipole molecule. Now this one is a permanent dipole having partial positive and partial negative end. While this was a non-polar molecule, but when the moving electrons of this non-polar molecule come in front of the negative end of this polar molecule, forces of repulsion operate. And because of these forces of repulsion, the electrons, their density increases at one end, while the nucleus, that is on the other end. So the force of attraction between partial negative end of the permanent dipole and nucleus are the positive part of the non-polar molecule, that is called as the permanent dipole induced dipole forces or Debye forces. Now these are momentary forces. Why? Because electrons keep on moving. When electrons come in front of this negative part, the polarization is created, induced polarity is created. But when the electrons will move away from it, again that molecule will become non-polar and its polarization will vanish. So these are the momentary forces, not permanent forces, because they form, they are vanished, they are formed, they are vanished. So that these forces are formed and vanished in the milliseconds even. For example, the forces of attraction between noble gases and water. Now, noble gases are the monatomic molecules, they are non-polar, and water is a polar molecule. So the polar molecules of the water induced polarity in the noble gases. They induce the polarity in the noble gases. And these are again a very important point for MCQs. These are the forces which are responsible for dissolution of noble gases in water. Now, keep in mind that if we see that which noble gas is more soluble in water, again a very important point for MCQs. Which noble gas has maximum solubility in water? So keep in mind that down the group in the noble gases, their water solubility increases. Now, why their water solubility increases? because their atomic size and the number of electrons increase. And greater the atomic size and number of electron, easier is the creation of the induced polarity. So a large atom with greater number of electron can be converted into induced dipole easily as compared to a small atom having low electron density. So these are the Debye forces. Now let us move towards the last part of the intermolecular forces. And they are the London dispersion forces, abbreviated as LDF, or they are also called as instantaneous dipole induced dipole forces. This one is their second name, instantaneous dipole induced dipole forces. Now, first of all, let me tell you that these forces are present in all matter, but they are particularly significant in the non-polar substances. For example, HCl. Now, the HCl is a polar molecule. Its major forces will be dipole-dipole forces. But London dispersion forces will also be present in it as the minor forces. But if you talk about the hydrocarbons like alkanes, alkenes, or alkynes, then their major force will be London dispersion force. So, London dispersion forces are the minor forces in the polar species and significant or major forces in the non-polar species, but they are present in all molecules, whether polar or non-polar molecules. So you can say, very important point, London dispersion forces are the universal forces actually. Now why they are called as London dispersion forces? Because Fritz London is a chemist who explained them. Dispersion because the electronic load is distorted or dispersed. Why they are called as instantaneous dipole induced dipole forces? Because actually the concept of these forces arises from the concept of liquefaction and solidification of noble gases. You know that noble gases can be easily liquefied and solidified. We know that noble gases do not form bond, and liquefaction and solidification is only possible when the gases or any species has certain intermolecular forces. If there are no intermolecular forces, that will be an ideal gas, and the ideal gases do not actually exist. So there are certain intermolecular forces actually, because absence of intermolecular forces means no liquefaction, no solidification is possible. If the noble gases can be liquefied or solidified, it simply means that there are some intermolecular forces present in them. And that was the idea that became the reason of the study of the London dispersion forces by the Fritz London. Now, the MCQ is asked from here that what are the forces which are responsible for the liquefaction and solidification of the noble gases? So that is the London dispersion force. Actually, one molecule is converted into an instantaneous dipole. Instantaneous dipole mean it becomes a dipole for very short duration of time due to distortion of its electronic load. Now this instantaneous dipole then disturbs the neighboring atom and it converts them into the induced dipoles, just like we have studied in the permanent dipole induced dipole forces. So the force of attraction between the instantaneous dipole and that induced dipole, they are called as the instantaneous dipole induced dipole forces. These are also the momentary forces. They are formed, they are short lived, they are formed for very short duration of the time. And now let us discuss most importantly what are the factors which affect the London dispersion forces. So the first important factor is atomic or molecular size. In atomic size, helium, neon, argon, krypton, xenon, radon. As you move down the group, the atomic or molecular size that increases. That's why helium has the lowest boiling point while radon has the highest boiling point among the noble gases. Why? Because greater the size, easier will be the polarization. More will be the polarizability. Mean distortion of electron of the larger atoms that becomes very easier. So greater the distortion of the electron or greater the easiness of the distortion of electron, that will give rise to the stronger London dispersion forces. Similarly, in case of halogens, fluorine, chlorine, bromine, iodine, astatine is also included. You know that these are all non-polar gases, but fluorine and chlorine are gases. Bromine is liquid and iodine is solid at room temperature. Now look at the difference in their physical state. It clearly shows that fluorine and chlorine have weakest intermolecular forces, weakest London dispersion forces, so they are gases, while the iodine has strongest London dispersion forces, so it is solid. Why? Because again down the group atomic and molecular size increases and distortion of the electron becomes easier. So the formation of instantaneous dipole and induced dipole, that becomes quite easy. And this can also be confirmed by their data of their boiling point. Like the boiling point of the fluorine is minus 188.1 degrees and that of iodine is plus 184.4 degrees. And you know the boiling point is always directly proportional to the strength of intermolecular forces. So looking into the data of their boiling point, it also confirms that fluorine has weakest while iodine has strongest London dispersion forces. So this one was the first factor, atomic or molecular size. Now the second factor which affects the London dispersion forces is the atomicity. Atomicity, that is also somewhat the molecular size. Like we study that in alkanes from C1 to C4 mean methane to butane they are gases. C5 to C17 are liquids and C18 and onwards are solids. Know why? Because they have very weak London dispersion forces, so they are gases. Then atomicity increases, molecular size increases, again the strength of London dispersion forces increases, and the hydrocarbon or alkane become liquid. And the further increase in their atomicity or molecular size from C18 to onwards, that gives them the solid physical state. And similarly, that can also be confirmed by their respective boiling points. Now, let me tell you one thing, that the boiling point of ethane, estimated boiling point of ethane is minus 88.6. Ethane is minus 88.6 degrees, while that of hexane is 68.7 degrees. Now look at this data. Again, it shows that smaller molecule with low atomicity has weak forces, so lesser boiling point, while the larger molecule with high atomicity has stronger forces and greater boiling point. The next factor is surface area, or you may say sites of attachment. Now, the strength of London dispersion forces is directly proportional to the surface area. Suppose that you have N-butane in which the four carbons are attached in series, while the second one is isobutane which is branched in which one carbon is out of the series. Both these they have molecular formula C4H10. So their atomicity is same, their electron number that is also same. But when we study their boiling point, it is seen that the boiling point of N-butane is high as compared to isobutane which has low boiling point. Why? Because it has greater surface area. It has greater sites of attachments, while it has lesser surface area, so it has lesser sites of attachment. Greater surface area gives rise to the stronger London dispersion forces. So that's why we say that normal alkanes, mean straight chain alkanes, they always have higher boiling point as compared to isoalkanes, mean branch chain alkanes. So normal alkanes always have high boiling point as compared to the branch chain. Now all these forces, dipole-dipole, ion-dipole, then Debye forces, London dispersion forces, they are weak intermolecular forces that are collectively called as the van der Waals forces. As far as the hydrogen bonding is concerned, it may be intermolecular or intramolecular. So it is out of the van der Waals forces, because van der Waals forces are purely the intermolecular forces. And now, if you want to study the hydrogen bonding, you can watch my video lecture on the hydrogen bonding and its application. That will also cover an intermolecular force. At the end, I will like to tell you the relative strength of all intermolecular forces. When we look into the data, with the energy which is required to break a particular force, it tells us that the strongest intermolecular forces are ion dipole forces. Then the second is hydrogen bond. Then the third is dipole-dipole force. Then Debye forces. And weakest are the London dispersion forces. This one is just a general trend of the strength of the intermolecular forces, but keep in mind the strength of intermolecular forces also depend on the nature of the molecule. Generally, this one is an approximate trend of the strength of intermolecular forces. Otherwise, you may see commonly that water has hydrogen bonding, which is written that it is quite strong force, but it is in liquid state, while London dispersion forces are present in iodine, but it is in solid state. So, this one is just a general trend. Strength of intermolecular forces also depends on the nature of the molecule that you are studying. Iodine, because of its very high polarizability, has so much strong intermolecular London dispersion forces that it becomes solid. While water has hydrogen bond, which is written here that it is a stronger force, so it must be in the solid state. But water has hydrogen bond, which is no doubt generally a stronger force, but here depending on the nature of the molecule, because of very high polarizability of iodine, the London dispersion forces of iodine are stronger than the hydrogen bonding of water. So this was all about the intermolecular forces. I hope so you will enjoy this lecture. We will come up with some new lectures next time, inshallah. Take care. Allah Hafiz.